In this video we're going to learn about the various different types of inverse that a function may or may not have. Here are the definitions. If you have a function f whose domain is x and whose codomain is y, then a left inverse to f is a function g from y to x, such that g composed with f is the identity on x. So it's called a left inverse because in that composition g is on the left of f. A right inverse to f is a function g from y to x such that f composed with g is the identity on y, and a two-sided inverse to f is a function which is both a left and a right inverse to f. We say f is left invertible if it has a left inverse, right invertible if it has a right inverse, and invertible, or two-sided invertible, if it has a two-sided inverse. Let's look at some examples of functions which do and don't have left and right inverses, beginning with the function f from the real numbers to the non-negative real numbers, whose rule is f of x equals x squared, and g, which is a function from the non-negative real numbers to the real numbers, such that g of y is equal to the square root of y. In that case, there ought to be some kind of inverse relationship between g and f, because squaring something is pretty much the inverse of square rooting it or something. So let's explore exactly what's going on there. In fact, g is a right inverse but not a left inverse to f. So to see that it's a right inverse, well, for any y in the domain of g, f composed with g of y is f of the square root of y, and that's just y again. That tells us that f composed with g is the identity function on the domain of g, which means that g is a right inverse to f. But g is not a left inverse to f. For example, if we look at g of f of minus 1, well, that's g of 1. And that's just 1 again. So g composed with f is not the identity on the set of real numbers, because the identity sends minus 1 to minus 1. It's even worse than this. F does not have any left inverse at all. If you suppose for a contradiction that a function h satisfied h composed with f was the identity on the real numbers, then because of that, h of f of 1 would have to equal 1 again. But since 1 squared equals 1, that requires that h of 1 is equal to 1. Now, playing the same game with minus 1, if h composed with f is the identity, then h of f of minus 1 must be minus 1 again. But minus 1 squared is 1, so this time we need h of 1 is minus 1. Now those two conditions are not possible because h can't have two different outputs for the same input. We have our contradiction, so there is no left inverse to f. And if you think about what's happened there, the problem was simply that f was not 1 to 1. That's where that contradiction came from. In the next video, we'll explore the precise connection between having a left inverse and being injective, and having a right inverse and being surjective. For some further examples, let's take this function f from 1, 2, 3 to 1, 2 with the rule that I've written at the top of the slide. Here's a picture of f using our standard function diagrams. What it does is it sends 1 and 2 to 1, and 3 to 2. So a fun thing to think about is, how do you do composition with these diagrams? I mean, you've obviously got to put the composition, put the other diagram for the function you're composing with on the other side of this diagram and kind of join them together. But how does that work? Anyway, the answer is a bit confusing, which is why I'm not going to talk about it now. What I will do instead is answer the question which I've written at the top of that slide, which is, what conditions must a right inverse to f satisfy? In other words, can we find whether f has a right inverse, and if so, what it has to look like? So g is right inverse, g is a right inverse to f if and only if, well, the definition is f composed with g is the identity on the set 1, 2, and that's true if and only if f of g of 1 equals 1 and f of g of 2 equals 2, And taking this one step further, well, what can g of 1 be? G of 1 must be something which f sends to 1. So g of 1 can be either 1 or 2. And similarly, g of 2 must be something f sends to 2. But there's only one thing f sends to 2, and that's 3. So actually what we see is that there are two different right inverses to f. So one function that sends 1 to 1 and 2 to 3, and another function that sends 1 to 2 and 2 to 3. Let's just draw those. What have you done? What's wrong with this picture? That had an extra 3. That's better. So what should the inverse to f, the right inverses to f do? They should have domain 1, 2 and codomain 1, 2, 3. And as we've seen, they've both got to send 2 to 3. But they can send 1 to 1 or 2. Those are our two different right inverses to the function f. So in particular, and this is an important thing to remember, that a function which has a right inverse might have more than one different right inverse. Let's look at a similar problem only for left inverses instead of right inverses. So this time g will be the function from the set 1, 2 to the set 1, 2, 3. Let's get it right this time. With the property that 1 goes to 3 and 2 goes to 1. So this is my function g. And again, we're going to determine whether g has any left inverses, and if so, what they have to look like. Well, h is a left inverse to g, if and only if h composed with g equals the identity on the domain of g. And that's true if and only if h of g of 1 equals 1 and h of g of 2 equals 2. Okay, so what can we say? Well, g of 1 is equal to 3, so I need h of 3 equals 1, and g of 2 is equal to 1. And I forgot to write if and only if there, that's better. Okay, well again you can see we've got choices, because this time there is no restriction on what h of 2 is. So there are two different possibilities for a left inverse to f, to g. Again, let's draw them. So what has to happen? Those left inverses are functions whose domain is 1, 2, 3 and whose codomain is 1, 2. And we were forced both times into sending 3 to 1, and we were forced into sending 1 to 2. But 2, on the other hand, there's no restriction on what your function does to that. You can send it any way you like. So you could send it to 1, or you could send it to 2. So again, if a function has a left inverse, it may have more than one different left inverse.